All right, we need to talk about density today. I decided to make a video to hopefully get through it a little bit quicker, and then that way you can pause it as you need to and write down anything you need. Now, these notes are going to be a little bit different. You definitely do not need to write every single word that you see. I'll tell you certain things that you definitely do want to write down. A lot of it is write down if you want, if you think it'll be helpful for you. But I'll tell you specific things that I for sure want you to write down. So let's get started. You should have your notebook, and this should be the title of your notes: classification of matter using density. If nothing else, at least have the word density there. That's the main thing we're talking about today is density. So essential questions, I would not write these down, but these are just sort of the questions that are going to guide us through what we're doing today. So first off, how does a change in mass and or volume affect the density of an object? Density is closely related to mass and volume, so we'll see how that works. How can density be used to determine if an object will sink, float, or remain suspended in a liquid substance, specifically water, since most things, water is generally the liquid that we think of. And then finally, how can density be used to identify a substance? We're going to do all three of those things today with these notes and the work that comes after it. All right, some vocab. Unless you don't know what some of these terms mean, I would not bother writing the definitions down. But the things that we're going to need to know about in order for this stuff to make sense today, we need to know what matter is. Matter is just a physical substance that's made of particles and occupies space. We're going to need to know what mass is. Mass is the measure of the amount of matter in an object. So the amount of stuff in an object is kind of the way to say it too. Matter itself is the stuff. Oh, come on, there we go. Matter is the stuff. Mass is the measure of the amount of stuff. And then we have volume, the amount of space that something takes up. And then finally, density. And we'll talk more about density. Density is one thing that we haven't really talked about yet. I don't know that you have a good definition for that yet, but density is just a measure of how much mass is in a certain volume. Usually the units are grams per milliliter or grams per centimeter cubed. In a couple slides, we're going to have more talk about density with this definition again. So if you want to write it down now, you can. But also we're going to see it more in a second. So just a couple more bits of information about these terms. Matter, again, physical substance. Mass would be what we think of as particles, and volume is how much space a thing takes up. For mass, the units we use are grams, and the tool we use to measure mass is a balance. This is a digital balance here. This is a beam balance. You may remember we used triple beam balances earlier in the year. Volume, again, we talked about earlier in the year. Usually our units are going to be milliliters if we're measuring liquid volume in a graduated cylinder, or we'll use cubic centimeters, centimeters with a little 3 above it, if we're measuring cubic volume. If we're doing that, then we'll just use a ruler and measure the length, the width, and the height, and then we'll calculate volume that way by doing length times width times height. If that's something you've forgotten, that formula to find volume, you might want to write that down. But it's pretty simple. And then here's our slide about density. So density describes a relationship between a material's mass and volume. Definitely write this formula down. Density equals mass over volume. We can simplify it by writing D equals M over V. This is a formula that you are going to be using a lot in chemistry, in physics. You'll use this a lot in science classes. So this is a pretty common, good to know formula. The other thing that you'll see sometimes is this thing called a density triangle. And we'll talk a little bit about how this works. But I would definitely write this down. Now, it's really important that you put the M on the top, the D in the lower left, and the V in the lower right. And basically what this does, you're not always going to be just solving for density. Sometimes you'll be given density and mass, and you need to solve for volume. Or sometimes you'll be given density and volume, and you need to solve for mass. And then you need to change up your formula a little bit. So you can use this triangle to help you figure out what formula to use. So let's think about this first formula, D equals M over V. To figure that out using this triangle, let's say we're solving for density here. Now I can't do it on the screen right now, but imagine you're covering up with your hand. If you have this written on a piece of paper, cover up the D, and then you'll see that what's left over is an M on top of a V. And that basically gives you this formula, D equals M on top of a V, D equals M over V. So let's say we instead wanted to solve for volume. If you cover up the V in this triangle, you're left with M over D. And that's the formula to find volume. Volume equals mass divided by density. So you can find that formula there. And finally, what if you need to solve for mass? If you've been given a density and a volume, but you need to find your mass, cover up that M, the thing that you don't know, cover that up, and what's left over is a D. This time it's next to a V. When we see them next to each other, that tells us to multiply. So here it would be divide because you have something on top of the other thing, just like if we were putting it in a fraction like this, M over V, M divided by V. Or M over D, M divided by D, but since we see them next to each other here, this is multiplication. So the formula to find mass is mass equals density times volume. Okay, hopefully that kind of makes sense. If that doesn't make sense, if you just Google density, you'll find all kinds of information and maybe some other tools that'll help you a little bit more with how to use this tool. Super helpful. So, last thing that I would recommend you write down is the units that we want to use. If you ever see grams on a number, that tells you that it is a mass. If you ever see milliliters or cubic centimeters on a number, that tells you that it's volume. And then I'll stop moving my mouse around so that that thing goes away. The density units that we'll use are, it's G/ml, but we pronounce it grams per milliliter or grams per centimeter cubed. So it's just the gram, the mass unit, with a slash, and then our volume unit. We determine which, and they're equal. 1 milliliter is the same thing as 1 cubic centimeter. So they're equal, meaning if I have a density of 1 gram per milliliter, you could also say that I have a density of 1 gram per cubic centimeter. They are equivalent. It really just matters if we're measuring a liquid, we'll usually use milliliters, or if we're measuring some sort of a solid, we'll usually use cubic centimeters. But again, they mean the same thing in reality. We just have to make it a little bit confusing, or else it won't be any fun, right? Okay, so next up we want to take a look at some pictures to illustrate density. So this is a really common way that you'll see density illustrated. You have cube A and cube B. They have the same size, the same volume. So you see their volume is 10, volume 10, but they have different numbers of dots in them, a different amount of stuff, a different amount of matter, which means a different mass. So this one has a mass of 20, and this one has a mass of 10. So when we calculate that out, doing density equals mass divided by volume, this cube has a density of 2, while this one has a density of 1. So we say cube A is more compact than cube B. Also, cube A has a greater density than cube B. Cube A is more dense than cube B. There's more stuff packed into the same amount of space, okay? Now, if we take a look at a different example, here we have the same amount of stuff. We have 20 mass units. We have 20 dots in both boxes, but the boxes are different sizes. So in fact, our density over here in cube B is greater. We have a density of 4 compared to our density of 2 over here. Okay, and so yeah, again, it's a measure of compactness. How much stuff do you fit in a certain amount of space? Well, there's more stuff compacted into this smaller amount of space. This is the same amount of stuff, but in a bigger space. So therefore, the density over here in cube A is actually lower. Cube B has a higher density because it has a kind of more stuff jammed into a certain amount of space. Okay, cube B is more compact, cube B is more dense. Finally, we can have different sized containers, but just because a container is smaller doesn't mean it's more dense. So in this case, if we do the math, the density in both of these cubes will be 2. We have a smaller cube here, but it also has fewer dots in it. Here we have a bigger cube, but it fits more dots in there. So in the end, they both have the same amount of compactness. This square happens to be 1/4 the size of this square, but this square contains 1/4 of the number of dots that this square contains. So in the end, the density is the same. Mass of 20 divided by a volume of 10 gives you a density of 2. Over here, a mass of 80 dots divided by a volume of 40 gives you a density of 2. So the same density, even though they're different sizes. Okay. Think of this like a chunk of wood. If I have a big chunk of wood and a smaller chunk of that same type of wood, it's still made of the same stuff, right? It's still the same wood. It's just a slightly, it's a different size chunk of it, but the density remains constant. This is kind of a weird concept. Sometimes this is really difficult for students to grasp. Do your best. Okay. Let's talk a little bit about the density of water. The density of water is interesting. So we're going to be figuring out whether things float or sink in water. So 1 milliliter of water has a mass of 1 gram. So let's do the math. What's the density of water? Remember, density equals mass divided by volume. Our mass is 1 gram. Our volume is 1 milliliter. So 1 gram divided by 1 milliliter, 1 divided by 1 equals 1. Water has a density of 1 gram per milliliter. Okay. Now, for one, lots of ones here. First thing to know is that this number is a constant for fresh water. Salt water is a little bit more dense. You may have heard that it's easier to float in the ocean than it is to float in, say, Lake Michigan or any body of fresh water. And that's because fresh water is a little bit less dense than salt water. Having that salt in the water makes the water more dense. So, anyway, any sample of fresh water will have a density of 1 gram per milliliter. At least it'll be pretty darn close. So if we know the density of a fluid, knowing that constantly water is 1 gram per milliliter, so we know the density of water, and if we know the density of an object, we can actually predict whether that object will sink or float on the fluid. So let's take a look at a couple of examples of that. So first off, we're going to look at a ping pong ball. Its density is 0.0840 grams per centimeter cubed. Again, water has a density of just 1 gram per milliliter. Remember, grams per milliliter, grams per centimeter cubed are essentially the same thing. Okay, so the ping pong ball has a lower density. This is less than 1, less than the density of water, so a ping pong ball will float on the water. Objects with greater density will sink. Objects, I wish that box would go away. Objects with a density less than water will float. If you're less dense, you're going to float. If you're more dense, you're going to sink. By the way, I would definitely write that down as well. Less dense things float, more dense things sink. Okay, I would not bother writing down all this stuff about the ping pong ball. Next, we're going to look at a glass marble. A glass marble has a density of 2.5 grams per centimeter cubed. Again, I would not bother writing this stuff down. And 2.5 is greater than 1, so a glass marble will sink in the water. Again, this is the same thing. Since the density is greater than the water, it sinks. Ping pong ball has a density less than the water, so it floated. Okay, let's. Ooh, I skipped something. Okay. Yep, this is the only one I skipped. So this concept works with gases too. It doesn't only work with water and solids. It'll work with gases too. So we're gonna watch this Mythbusters video to illustrate something real quick, and then I actually want to show you something that you can do at home to illustrate this or show this to your family. It's pretty neat. But first, so the density of normal air is 0.0012 grams per milliliter. So pretty light. Much less than water. That's why water sinks in air, right? If you drop water in the air, it falls to the ground because the water is more dense than the air. So densities of some other gases, helium, you can see is a lot less dense. There's 3 zeros here, only 2 zeros here. That's why helium balloons float. Sulfur hexafluoride is what they're going to show in the Mythbusters video. That's more dense than air. You can see 0.006 as opposed to 0.001 for normal air. And then carbon dioxide is a trick that I'm going to show you. That's a little bit more dense than air. Instead of 0.0012 for normal air, carbon dioxide is 0.0019, even maybe 0.002 grams per milliliter if we round. So let's watch the video and then I will show you the cool trick here. We're going to do it this way. Hopefully you'll hear the audio okay. In case you don't hear the audio, you can just Google this, Mythbusters floating on invisible water, and hopefully you'll be able to see the same video.
I promise to show you something really cool as long as you promise not to try it at home, okay? Okay. Now, everyone wants why my voice sounds higher when I inhale helium.
My simple fact is that helium is 6 times less dense than air, which means sound waves travel through it much faster, which makes my voice sound much higher. Now, the same effect can be achieved in reverse if I inhale something like
sulfur hexafluoride, which is 6 times denser than air. I inhale some of that. And yes, that's why I live, and somehow I'm still funny. It's scientific!
On that low note, it's time to start the test and flush out this potential viral flim-flam.
Now that we've got the gas, I want to replicate exactly what I can see in the video. We got a fish tank and we got tons of tin foil. I'm going to try and make a boat that floats on the invisible water. All right. Give me the business end. I can't see anything.
We'll have to take the full tank on faith, just because we can't see anything. Now, Adam turns boat builder.
All right. Replicating the circumstances. You ready?
It's a simple proposition. The boat either floats or it sinks. But Jamie can't see why this won't work. And here's the proof of concept.
There you go.
So that's where our level is.
Right, somewhere right about there. Let's just be clear. This balloon is filled with air. And it drops. Unless it's in this fish tank. Where it floats. Because the fish tank's full of a gas that's heavier than air. I just can't get a boat to float in it. As pretty as it doesn't.
Okay, so hopefully that video worked okay for you. And I'm going to switch over to my camera here to show you a cool thing that you can actually try at home. So, make sure I'm not knocking everything off my desk. You guys have probably all done this before, right? You take some baking soda, you take some vinegar. Sorry, this is actually, you know what, can I do this? There we go. Now it looks like English. So you take some baking soda, you take some vinegar, and you put them together, and you probably know what happens, right? Well, I'm going to do that real quick. So I've got some baking soda in my beaker here. Here's some vinegar. And I'm probably going to make a mess, but that's okay. Yeah, there we go. Dump it on my floor, whatever. It's no big deal. You should do this over a counter or something, probably, but I've already got a bunch of it on my floor anyway. So here's the cool thing. When it bubbles like that, what it's making is carbon dioxide gas, which, if you remember, we said was a little bit more dense than air. So I've actually got a beaker full of carbon dioxide gas right here. And I've also got this candle. So the cool thing is I could actually pour this gas out like it's liquid. I won't breathe on it. I just poured that gas out as if it was liquid. Candles, flames need oxygen in order to burn. You can sort of suffocate a candle by putting carbon dioxide gas onto it. So that's what I just did. I poured gas out of this container onto the candle to stop it from burning. It's actually kind of how fire extinguishers work too. Some fire extinguishers work by basically making a cloud of carbon dioxide gas, which essentially suffocates the fire. So that's a fun thing you can do at home to show that carbon dioxide gas is more dense than normal air. So what I'm going to do is stop the video here and make another video so you can go take a look at the second video where we're going to do some example problems to actually calculate density. All right, so go watch that next video with the practice problems.